thanks to everyone who are going to listen my talk. So my name is Saqib. I'm associate professor in Department of Energy Technology, Aalborg University, Denmark. So my today topic is hydrothermal liquefaction process, and in this process I'm working since more than 10 years, including my PhD from 2007 till now. So first of all, I will just give you some geographical information about my country, that is Denmark. So it's very small country in Europe, in north of the Europe. So you can see here, and the capital is Copenhagen. Maybe some of you guys already know, very famous capital. And total population of Denmark is 5 million only 5 million. So right now I'm sitting here in Aalborg, that is on the north of Denmark. And if you look at the city, so it's very beautiful city, Aalborg city. It's Denmark's fourth largest city, and population is almost 500,000 people. So we have small fjord going in between the city. So in the two parts, that Aalborg city. So we have three campuses of Aalborg University: one in Aalborg, one in Esbjerg, close to the Germany border, and one in Copenhagen. But most of the engineering and technical sciences we have here in Aalborg, and also some of in Esbjerg. So this is a quite young university, 1974, so almost 22,000 students. And according to the US News World Ranking, so we are at number 250. And we are one of the best in Europe, especially in the field of engineering. So if you look at the aerial view of our campus at Aalborg, so this is all which I circled with the red line. So this is Aalborg University campus. And if you want to see my department, so this is energy technology. So these buildings are for faculty, for the researchers, and for the PhD students. And these are our workshops, our labs, and our pilot plant, in which I'm also working on the biofuels, and these are our labs. So Department of Energy Technology, Lasse Rosendal is head of department. I think he became head 1 year before, and he's my previous PhD supervisor. And I'm working with this guy almost 14-15 years. So if you look at the energy technology, you can see most of the disciplines are related to the power electronics, power systems, electric machines, fluid powers, thermal energy system. And we have very small research group, advanced biofuels. And all the groups also have definitely the lab facilities, and our lab facilities name biomass conversion facilities. So we have 2 labs. In the next slides, I will also tell you about the labs. So we have the faculty of almost 60 members and close to 100 PhD. We also welcome guest researchers from all over the world, and 30 almost technical persons, and almost 300-400 students, including the master students. So if I will talk about my advanced biofuel group, so our head is Thomas, associate professor, and I'm also associate professor. Then we have 1 assistant professor, 2 postdoc, and almost 6-7 PhD students. And we have also master students who previously worked with us. We have our chemical engineer NA in the lab, and we also have more than 5 mechanical and technical staff. We have also some former employees, industrial PhD student, and other PhD students. We also have some guest researcher recently. Luckily, one from Canada, Charles Zhu from Western University, and also Professor Xiaongong Deng from Arizona State University. So we also welcome all the guest researchers to work with us in advanced biofuels research work. So our objective and goal. So our objective is to take the waste biomass and then convert into valuable products by using hydrothermal liquefaction process. So our main target is to produce the biocrude, the bio oil, so that we can use it as a transportation fuel. definitely after the upgrading. Then we are using the wet biomass mostly. The requirement of the process is, it's by name hydrothermal, so we have a lot of water in it. So definitely we have byproduct in the form of water, then biochar, then more than 85% CO2. And we can use all the product in different applications: value-added chemicals, biochar as a biofertilizer, then heating, and also definitely as a transportation fuel. So we are mostly giving stress on the food security without expanding any land use. So no need to use the crops. That is a direct connection with our food. So we are not in favor of the first generation biofuels. And definitely if we are using the waste, so we are going to reduce the waste burden on our society from the environment. And we are going to provide the clean energy without increasing any greenhouse gas emissions in the environment. And that is the big problem nowadays for our planet. So before explaining about the liquefaction process, little bit about the world energy outlook. We are very thirsty people nowadays. We are using lot of energy in form of transportation, in form of industrial sector. So world energy consumption, if we see at the current situation, so from 2018 to 2050, it will increase nearly 50%. And mostly it's non-OECD countries because of their strong growing growth and definitely the rise in the population. So we are consuming a lot of fossil fuels from 2018 and definitely in the future. If we look in terms of the sector where we are using fossil fuels more, so it's definitely in the industrial sector. That is refining, your mining, agricultural sector, in construction sector. So the rise will be almost more than 30% from 2018 to 2050. And definitely also in the transportation, commercial and residential sector also. So if we are consuming a lot of fossil fuels and energy, so definitely we are emitting a lot of CO2. And this is a very common understanding. So from 2018 to 2050, we are increasing at an average rate of 0.6% per year. And definitely, as I said, non-OECD countries are using more fossil fuel, so definitely they are producing more CO2 emissions. And most of you guys know the 2-degree scenario in the Paris Agreement on the climate change. If we follow that one, then it will be good for our planet. Otherwise, the current indicators, we will increase the temperature in the end of this century, 3.5 degree. If we will not take action, so it will be rise up to 4.5 degree. And there will be catastrophic changes in our planet in terms of floods, for our wildlife and everything, for our crops, for our land. So that's why we have to think about why we are using so much fossil fuel and why we are not controlling our CO2 emissions. So what will be the solution? We have to think about this one. So one good thing from COVID-19, so one good thing only, so it's the coronavirus triggered the largest ever annual fall in CO2 emissions. Why? Because of the less mobility of people in the transportation sector, in the aviation industry, in the road transportation. So actually it was expected to rise more than 1% in 2020, but basically it decreased up to 6% only due to the less mobility of people, less mobility of the people due to the COVID-19. And if you look at the big cities in the world, so how much decreased the NOxes in the air? So we definitely improved the quality of air by not using a lot of fossil fuel during the pandemic situation. So you can see the effect. So this is the evidence. If we reduce the use of fossil fuel, definitely we will reduce the CO2 emissions and we will save our planet. So what will be the solution? Definitely we should depend on the sustainable and renewable sources. But why? Because it's sustainable, you can produce again and again, only source of renewable carbon. Because in terms of the burning of fossil fuel, basically you are releasing the ancient CO2 which is stored underground million of years before. But in terms of the burning of the biofuels, basically you are releasing the fresh CO2 cycle which is stored in our plants. So that's why net reduction of the climate gases will be zero in terms of CO2 emissions. We have plenty of renewable sources, you know, the wind turbines, photovoltaics, our hydropower. Then I realized, and it's the common thinking, biomass is the only source that can provide liquid fuel as well as heat and power, and definitely value-added chemicals. So this is the single biomass. This is a single renewable source from where we can get different type of energies. So renewable energy becomes the leading source, especially in Denmark. We stress too much on the green energy, and Denmark is also very famous in terms of the wind turbines and in biogas production. So from 2050, increases will be almost 3% per year between 2018 to 2050. So you can see there will be increase in the trend in the renewable as compared to the petroleum and other liquids. And there will be 32% primary energy consumption, petroleum and other liquid decline from 32 in 2018 to 27% in 2050. So you can see this one. And definitely there will be less dependency on the coal, because in Europe, mostly we are going to close the coal power plants, and we are using the wheat straw and the biomass gasification and these term of renewable energy. So that's why there will be also a reduction in the consumption of the coal. And if you look at the transport accounts almost 32% of the final energy demand. And in that 32%, 96.7% come from non-renewable energy, that is your fossil fuel. Only 3.3% came from renewable energy. And in that 3.3%, only 3% biofuels and 0.3% is renewable electricity, that is your electric cars. And this 3%, definitely the most dominant biofuels are your biodiesel and bioethanol. For example, in US, in Brazil, the bigger producer of bioethanol and biodiesel, especially the bioethanol. So this is really a general acceptance from everyone that biomass was the precursor of the petroleum fuels. And definitely photosynthesis is the green engine of biomass. And this is because of the photosynthesis, we have oxygen in our biomass. So if we look at the petroleum, we have mostly hydrogen and carbon, not the oxygen. So the question is how we remove this oxygen so that we can get only our carbon and hydrogen. And this is common consensus that due to the tectonic activities, our biomass and dead animals just buried under the layers of the crust material, and by increasing the temperature and pressure, it converted into the fossil crude. But in case of biomass, we have the living plant, we have the waste, animal waste, and sewage sludge, these type of things. So only problem is oxygen, how we can get rid of this element. And we have plenty of non-food resources, primary residue from the agricultural residue, forest residue. We have secondary from the pulp and paper industry, for example, the black liquor, sawdust, from the sugarcane industry, slaughterhouse, animal manure. We have tertiary residue, municipal solid waste, and some of the energy crops which we grow by ourselves, the jatropha, miscanthus, and sweetgrass. And definitely we have sewage sludge and all the micro and macroalgae. So we have plenty of biomass sources that don't have any connection with the food. So we have to get advantages from them. And each biomass has different chemical composition, different proximate elements, and ultimate analysis of the feedstocks. So we have cellulose, hemicellulose, lignin, and some, for example, from microalgae, we have crude protein, crude fat. So all biomass has different chemical composition. So we have to think about all these biomass in a different way before we are going to process in a specific kind of process. So I just give you one very good example, I think, from the Boeing company in 2006. It's a very old example, but still it's a valid example, I think. So we are not in favor of first generation biofuel. Why? Because if we need for the world airline fleet, if we use 100% biojet fuel from soya bean, so it would require 322 billion liter of jet fuel per year. So for this one, if we are going to produce from the soya bean, from the first generation biofuel, so you need almost 575 million hectare of the land to grow the soya bean, then you can fulfill the demand of this one. And it will be almost the size of whole Europe. So you will only grow soya bean if you are going to fulfill this demand. So with respect to this one, if we look at the second or third generation, for example, the microalgae, we put the same scenario and same amount, 322 billion liter, we only need almost 35,000 square kilometer. And that is only the size of the Belgium, the very small country in the Europe. So this is a big difference in terms of the production and in terms of the cultivation of any crop, the competition between the first generation and the second generation. And in terms of the lipid contents, algae is much better as compared to the soya bean. And you already know we have different conversion options for the biomass to convert into secondary energy carriers. So we have thermochemical conversion domain, we have the biochemical, and then we have also the esterification for the biodiesel, then fermentation for the bioethanol, then we have biogas, then combustion, very old technology, just burned anything biomass and then you can get the heat. Then gasification for the production of syngas, and here where I am working on the liquefaction and also the same process. Not the same, because in pyrolysis we are using the dry biomass, in liquefaction we are using both dry and the wet. But the production and the products are almost same, the gas, the bio oil and the char, which we can upgrade it and use it as a diesel, as the fuel for our transportation fuel. So biomass transformation chain also have key issues in all the areas, in the feedstocks, in terms of cost. Is it cheap? Is it expensive? What will be the quality? Either we can convert it or we can't convert it in terms of the quality, its availability, its location, transportation, everything. Then in terms of technologies, what will be the status of technology, capital cost, our capex, our opex, and then yield, then efficiency, then scale, then byproducts. Then definitely we will look at in the products, what will be the value of product if we are going to produce some specific kind of renewable biofuels. Then we have to look the market, either market has demand or not demand. Then competing routes, definitely we have competition with the biodiesel, with bioethanol and all these kind of biofuels. Then quality specifications, either we are going to meet the standard specifications from the customers, and also the green credit. So are we really reducing the CO2 emissions in terms of the renewable or sustainable technology and the green credits? So why not biodiesel and bioethanol? One thing always remember, biodiesel and bioethanol, they are oxygenated fuels. Believe me, I'm not enemy of these technologies, but I'm just giving you some realities. Biodiesel and bioethanol, they are oxygenated fuel. In biodiesel, you have more than 10% oxygen. In bioethanol, you have almost 30% oxygen. So we can't use biodiesel directly as a jet fuel. You can see its freezing point is almost close to 0 degree. And when you are going on high altitude, so it must remain in fluid in order to be pumped. Otherwise, it will be a disaster for your flight. Because for the conventional jet fuel, it should be minus 40 degree, the freezing point. And I'm not going to read all these disadvantages of biodiesel. That is the technical challenges in terms of the NOxes, stability, hygroscopic nature, thermal degradation at elevated temperature, low energy content, and performance related, definitely corrosion of the fuel injection, because in your engine, you don't have only the metal, you have some rubber parts. So that will be also affect on your some parts of the engine if you are using the biodiesel 100%. Definitely you need some blend. In some countries you have 20% blend. It's according to the legislation from the government how much you can blend in your fossil fuel. So if you are going to use 100% biodiesel, you have to modify your engine, because the company, the automaker will not give you the warranty of the parts without the permission of the automaker, how much you have to blend in your car. So that's why there is some limitation in terms of the blending of biodiesel and bioethanol. So for fuel criteria, it's very important to fulfill the criteria if you are going to send your fuel into the market. So its suitability, that is totally related to the physical chemical properties of your fuel. It's totally related to the performance, the emissions, the durability of engines, so all these things. And the second thing is sustainability. So this is totally food versus fuel competition, and supply and the cost of your fuel, and definitely the net CO2 reduction. And the last but not least, the industrial capability. So it's the life cycle analysis of fossil fuel versus the life cycle analysis of your biofuel. Then the already existing infrastructure and drop-in fuels. I will explain in next slide about the drop-in fuel concept. So this is a fuel criteria before going to produce any biofuel. So now come to the point, the hydrothermal liquefaction. So this is very effective and promising technology to valorize the different type of wet biomass, and definitely the dry one. If you are going to use dry one, you have to put the water by yourself, fresh water or any water, because it is the demand of the process. So ranging from lignocellulosic to algae and organic waste like municipal solid waste and then sewage sludge. So these type of organic waste. We are using water as a reaction medium. So maximum temperature from 250 to 450 degree, and pressure from 100 to 350 bar. So at this temperature and pressure, you know the water will be at supercritical conditions. And when water is at supercritical conditions, it will behave entirely different with respect to room temperature, because at supercritical temperature, the water has very low density and very high ionic product. So because of these switching in the properties, you will promote the ionic reaction rather than the free radical reaction. So you will get more oily like components instead of char and gas. And definitely your dielectric constant will also decrease. And then most of the organic and gases will also dissolve in the water. So it's the beauty of water as supercritical conditions. And the main product, we are getting the biocrude, then solid residue. Definitely we have inorganic in our biomass. If you are using the sewage sludge, in sewage sludge we have a lot of ash content, so definitely you will get a lot of solid residue in the end product. Then we have water soluble fraction like ethanol, methanol, and some acetic acid and acetone, these type of dissolved organic in the water fraction. Then gases, and most dominant gas in the HTL gas product is CO2. Why? Because most of the oxygen from the biomass we just capture from it and convert into CO2 by two famous reactions, that is dehydration and decarboxylation. So we convert our biomass oxygen into CO2, and rest of the gases are in traces, that is your little bit methane and also the hydrogen and some small hydrocarbons, so these type of gases. So what we do, we take different kind of biomass, we make an ideal recipe, the slurry. Then we put into the reactor. Then we get our bio oil or biocrude, that is the raw biocrude. This is not able to run into the engine, especially in the cars. So it's a raw biocrude. So we need its upgrading by adding hydrogen and remove the rest of oxygen, because rest of oxygen in biocrude is almost 3 to 5%. And then we compare our oil with the rest of the normal crude oil and the diesel. So the green one is raw HTL oil and the gray one is our crude oil. So you can see we have a lot of oxygen as compared to our fossil crude. So we have to reduce this one by the upgrading, and we also reduce the density, reduce the viscosity in terms of the pumpability, and we have to increase its heating value. And sulfur contents, we have very, very low sulfur content in our HTL biocrude. So in terms of sulfur contents, HTL biocrude is much better than fossil crude in terms of sulfur contents. So in the lab scale, we take, for example, the dry straw or any biomass feedstock, we make the slurry. We have very small microreactors, almost 50% dry matter or 20% dry matter. It depends on the size of the reactor. Then we also put some catalyst to increase the yield. It depends which type of feedstock. So mostly catalyst has a significant effect in terms of the lignocellulosic, not in the protein containing biomass. But I'm not going to go in detail why this effect happened. So then we close our reactor, we do the leak test, we put the pressure transducer, we dip in our already heated sand bath, which is at 375 or 400 degrees C, our HTL conditions. Then we have the shaking device. Then after 15 minutes of retention time, we just take out the reactors. We have all the temperature and pressure from LabVIEW software. We keep eye on the process, and after this, we open the reactor and we collect the gas product. So we do the gas analysis in the GC analysis in the GC instrument. Then the collected product, we have oil. Then we clean our reactor with the acetone, because acetone is very good solvent to become to make the oil soluble in the acetone, so that we can rinse out all the parts of the reactor. And then we do the vacuum filtration. We separate the solid with drying, and then we get the solid residue. You can see very small amount. Definitely we are putting almost some gram of the biomass. Then oil, acetone, and water phase, we use the rotary evaporation, and then we add 2-3 ml of diethyl ether to separate the water phase, and we have our oil phase in the end. So we do all the characterization, GCMS, heating values, CHN, Cole-Fisher, the water contents, the sulfur analyzer. We used all the techniques for all the products which we are getting from the HTL on the lab scale. We published many papers, and you can see we use many different kind of biomass: eucalyptus, swine manure, sewage sludge, waste cooking oil, contaminated construction wood waste, high ash containing sewage sludge, barley straw. So we tried many feedstock just to see the yield of oil from these kind of the biomass wastes. So this is the picture of our analytical lab. So we have almost all the instrument for biomass characterization, biomass ultimate analysis, proximate analysis, heating values, everything. And then this is our production lab. So in production lab, we have reactor, we have distillation column, we have hydrotreater, we have autoclave, centrifuge, so everything. So here you can see we have from 5 to 42 ml system of the micro batch reactor for parametric studies. So we can change the temperature, pressure, retention time, water to biomass ratio, catalyst. So everything we do the parametric studies with different kind of feedstocks. We have autoclaves. We have 1 liter system, semi-continuous system. Then we have hydrotreater. So from biomass analysis, production, separation, upgrading, and end use application, we have all the instrument in our lab. So these are some pictures from, this is our micro batch reactor setup, then autoclaves, evaporator. This is big rotary evaporator. We use this one when we run our pilot plant. I will show you the pictures of pilot plant and the specification of pilot plant in next slides. So fiber analyzer for the proximate analysis of the biomass in lignocellulosic, especially cellulose contents, hemicellulose, and all these things. So we have also a hydrotreater for the upgrading of our biocrude. We have the distillation column. So after the upgrading, we put it here. This is the same concept in the petroleum refinery. The distillation column, put the crude oil, you get the different boiling point cuts, the diesel, petrol, kerosene, jet fuel, and everything. We have small test stand for the diesel engine testing for our biofuel, if we have the diesel range. And we have very beautiful and very compact mini jet turbine for the testing of the biojet fuel. Okay, so now after the lab, we have our HTL pilot plant. So this is the collaboration between Aalborg University and the Steeper Energy. And as I said, this is a Danish-Canadian company. So it's a collaboration between Canada and the Danish guys. And we commissioned in almost 7 years before. So capacity is 20 kilogram per hour feed, continuous processing. So operating condition 450 and 350 bar. So it's really robust technology. So more than 1200 hour of oil production. So we put everything in the containers due to the limited space at our campus. So everything in the container. I show you pictures in next slides. So recently we have the partnership with the Silva Energy, that is the Norwegian Swedish joint venture. And we are going to construct industrial scale demonstration plant in Tofte in Norway. Why in close to the Norway and the Sweden? Because Sweden, you know, it's very famous in pulp and paper industry. So a lot of forest. So we will use the forest residue for HTL process. So the cost is almost 50 million euros. So our target is to produce almost 30 to 100 barrel per day biocrude. So expected, I think in 2021, it will be operational, hopefully. So if you look at the process flow diagram, the feed barrel, increase the pressure by the compressor. We have multiple heaters sent into the reactor. As I said, due to the limited space in the container, we have 2 reactors parallel instead of 1 big reactor. Then we cool down the product. We reduce the pressure by the capillary section, then remove the solids from the filter, the section, some of the product from the filter here, then cool down, and then we have the gas analyzer for the analysis of the gas. Then we have the main product here. So you can see feed pump, heaters, our 2 reactors, and capillary section to reduce the pressure. And this one is our small hammer mill. If we have dry biomass like the forest residue, we will just grind here and make the slurry here, mixture of biomass and water. So it's a kind of extruder to make the slurry. Then we send this slurry here to our second container. This is the big mixing tank. Then we send into our reactor system here. Then we have 2 separation tank. This is the same 3-phase separation. We have the gas, then water, then the oil, and we collect in different barrels. So this is our control room. And then recently we did a pilot plant campaign of municipal solid waste. So we collected some of the biopulp. We called it biopulp because the company Gamidan, I visited there, and they took all the garbage from different municipalities and they put in a big digester. So 1 ton of garbage and half ton of water, they mix it and then pass through the 6 millimeter sieve. Then they get this biopulp. This is very, very nice and ideal feedstock for our pilot plant for HTL process because it contains 80% water, almost 1% ash, fat contents 19.40. You know, it's coming from household, so definitely some food things. So fat content, heating value is 18. So we did the pilot plant campaign, and then the oil recovery is almost 45%, energy recovery in oil fraction almost 85, and carbon recovery from biomass to oil, it's almost 70%. So it's really nice data we obtained from the pilot plant by the municipal solid waste campaign. And when we compare our raw biocrude, not the upgraded, the raw one, so it's almost the same like the bunker fuel, the marine fuel, which we used in the heavy ships in terms of carbon, hydrogen, nitrogen, and sulfur. Only the problem is oxygen. So you can see oxygen is almost less than 1% in the bunker fuel. In our case, it's almost 5%. So we have to get rid of this one. So that's why if you, for any fuel criteria, you have to make the Venn Cleveland diagram so that you can see the quality of your oil. So more on the left side and more on the top side, the fuel will be the good one. So this is our crude oil standing here. This is our bunker fuel, and this is our diesel, which we put in our cars. So biomass feedstock are standing here, and we are right now here. This is the solid green point from our Wood Albo University continuous bench scale system. That is our pilot plant. So our main objective is to reduce the dehydration and more decarboxylation. So we are going to sacrifice carbon, but not the hydrogen, because by increasing the hydrogen content, we will be more on the left and the top side. So our objective is going here by the upgrading of our biocrude. So you can see how thick is our biocrude from the pilot plant. So this is raw biocrude, very viscous. And then what we do the upgrading in our hydrotreater. This is our in-house built hydrotreater. And you can see visually the color, and in terms of the chemical components, before the deoxygenation and before the denitrogenation, almost 30-40% we have our aromatics, paraffins that are good components in our oil. But after the deoxygenation and denitrogenation, you can see we have up to 60-70% our aromatics, naphthenes, and paraffins. And these are our hydrocarbons, which are good for our oil quality. So that is the beauty of the upgrading of the biocrude by using the hydrotreating process. And it is the same process which we are using in the petroleum refinery for the heavier fraction of the crude oil. So after the upgrading, definitely we will use the distillation column. So this is our this is written in Danish, so it means the waste from the trees. So agricultural, not the agricultural, it's the forest residue or the waste from the trees. So this is our water and oil. After the separation, we have upgraded oil from the hydrotreating. Then we put this sample or this product here in the distillation, and we did atmospheric and vacuum distillation, and we get the different cuts, same like in the petroleum refinery, at different temperature in terms of petrol or diesel and kerosene. And in the end, we have the heavier fraction, the boiling point more than 350, just like the bitumen in the fossil crude. Then we compare our results with the as a benchmark with the Brent crude. So this solid line is the simulated result from the hydro denitrogenation without the deoxygenation. And then we did with our true boiling points. So it's almost following the same trend. But after the upgrading, after the first upgrading, you can see we can increase the quality of our oil and very close to the Brent crude that is already a commercial one as a benchmark. So then we can see how we can have different cut of naphtha, diesel, and the fossil, and then our vacuum residue. So now it's on us where we can drop in our fuel. If our fuel is good enough that we can send to the petroleum refinery and we just mix with each other and we check the miscibility and we get the different cuts, the diesel, kerosene, naphtha, and petrochemical. Or maybe we can directly use our the raw biocrude, not the upgraded, the raw one as a bunker fuel, as I mentioned, and compare the properties in terms of carbon, hydrogen, and nitrogen contents. Or maybe
Dr. Saqib, I was just going to say we have 15 minutes left, so if you want to...
Yeah, I'm going to finish maybe within 5 to 10 minutes.
5 to 10 minutes. Okay, so that will just leave a couple minutes for comments.
Yeah.
Questions.
So then we can upgrade and get diesel or maybe the kerosene. So now the question is how we can integrate. Definitely, it's very important in biorefinery concept to integrate our HTL with the multiple energy technologies and mass flow. So the good example is you can produce the biogas from the manure, organic waste, or the municipal solid, the sewage sludge. You can put it here, but after almost 20-25 days, you will have no more production of biogas. So it will be steady state. So it's better to use this digestate and directly sent into the HTL and produce the biocrude. And the water you can sent back to the HTL or maybe into the digester, because it contains very good organic, it will be act as enzymes and for more production of the CO2. So the research challenges, definitely nowadays we are trying to mix different feedstock. For example, the cow manure with the algae, then wood with the sewage sludge. So we are going to check the synergetic effect in the HTL process, and it is really challenging. And process chemistry, if you go into the literature, very few study you will see on the chemical kinetics and reaction kinetics of the HTL process, mostly on the model compounds. And for high efficiency conversion, you need high dry matter content, but then you more work on the mechanical point of view on the pumpable feeds. You need very strong pump to pump your feed into the HTL process. And then definitely the efficient upgrading from the biocrude to transport grade biofuel. So in the end, we have completed many advanced biofuel projects with different our partner. You can see one of from Canada, from the natural resources, for a very big project, almost 4 million euros. We finished 2 years before almost. And recent, we are working on Ford Finery, next generation road fuels, and high flex fuel. In Ford Finery, we are using all the forest residue, agricultural residue, like wheat straw, eucalyptus, pine wood, and these type of things. In next generation road fuel, we are working on the sewage sludge. We are working on municipal solid waste, that is biopulp, and we are also working on other kind of the waste. So take home message, wet waste are available everywhere and no need to invest to grow the energy crops, because you need the land and then you have to grow, then you have to wait, then you will cut, then you will do the process and get the biofuel. So it's better to get the waste and do the process and get your biofuels. And agricultural and livestock sector produce abundant amount of biomass in form of residue, animal waste like bagasse, the rice husk, cow manure. Big city produces millions of tons of municipal solid waste, and it's a big problem for the municipalities and for the society. And sewage sludge also. And hydrothermal liquefaction is a promising and I think sometimes only viable technology for some wet waste, because we have a lot of wet waste like municipal solid waste, sewage sludge, animal waste. So this technology is really promising in terms of the biofuel production. And definitely drop-in advanced biofuel for the circular economy, sustainability, and carbon negative production. I have very strong belief in terms of the collaboration, so that we can bring the people together. As from our different projects, you realized we have many partners, so we can learn from each other by sharing knowledge and research. I would like to collaborate with the Dalhousie University, your faculty, both in terms of research projects and also the exchange student program, because we have many exchange students, we have guest researchers. And the last thing, nowadays we have a Marie Curie postdoctoral fellowship call. So if any of PhD student is interested, so it will be my pleasure to become his potential supervisor in this call, so he can apply and submit the project proposal. So it's fully funded 2-year and extended up to 3-year postdoc fellowship. So deadline is 17 February for the talent course, but the actual deadline for the complete application is 15 September. So thank you very much. So this is our group photo, our research group in front of our big, not big, small pilot plant. Thank you very much.
Wow, thank you. Wow, it's not very often that our students get such a good offer in a talk, in addition to such substantial work, such intriguing directions for society that your lab is taking on. So any students on the call, please share that opportunity with others as well for a postdoc with a very engaging and promising field of research. So it is a delight to have you join. So I'm going to open up the floor to any participants on the call who would like to ask Dr. Saqib directly any questions. Please feel free to unmute yourself and ask a question.
Yeah, can I ask a question?
Yeah, sure. Welcome.
Thank you, Saqib, for such a nice presentation. It was so like interesting, and I just have a question. Like you told us a lot about the research areas and all those things. I'm just thinking whether your lab also have something related to implementing these things in using some IT or programming things. Like, do you have some computer scientist part also in that or not? Like nowadays in agriculture, for the precision agriculture, this becomes a little important thing. So is this happening in your department also or not?
Unfortunately not, but some of our PhD student, not some of, I think one student, he's working on the life cycle analysis. You know, in life cycle analysis we cover all the areas in terms of the production of the biomass feedstock in agricultural point of view, and all the parameters we covered in life cycle analysis. And some of the guys we have in the planning department, but not in our department. So our department is totally related to, as I said, more than 90-95% it's power electronics and these type of guys, wind turbines, photovoltaics, hydrogen fuel cells, and a small portion from our advanced biofuel. But our research group, unfortunately, they are not working on IT and these type of instrumentation which is related to the agricultural activities or cultivation and these type of things. Not unfortunately, we don't have. Yeah, but we have in connection with different companies, with different suppliers. For example, in terms of municipal solid waste, as I mentioned, there is a company Gamidan. So we have a connection in this way. Yeah.
Great question, Imran. Thank you for that. Humphrey, I think you had a question.
Yes, sure. Thank you very much for the presentation. So we wanted to find out for your HTL process, how much energy are you consuming during the process as compared to how much you're getting from your biomass at the end of the reaction?
Yeah,
I think that's a very important factor in
yeah, it's very important and it's very good question. Yeah, and I faced this question many times in conferences and everywhere. We didn't do any heating integration and energy balance and the mass balance in an efficient way. We didn't do this one right now. As I told you, we are on a lab scale and little bit on the pilot scale. And the company Steeper Energy, that is the joint venture between Canada and the Denmark, they have all the information and it's the confidential information, as they are going to start their operation in Norway, the bigger demonstration plant. So definitely they have all the numbers and the data which you asked from me. But definitely if you are going to heat up at 350 and 400 degrees C temperature, which contain almost 75% water, definitely it's a very intensive energy consuming process. But by doing the heat integration, by utilizing your byproduct, for example, if you have hydrogen, and by recirculation of the water phase, we also do some recirculation, you can optimize your process. So nowadays we are also thinking to hire a PhD student or postdoc which will work on all these you know, the ESPN simulation calculations and energy flow and the mass flow and all these TEA, that is techno-economical analysis. So we are working on this one. Yeah.
Excellent. Thank you, Humphrey. Reem, please.
Thank you, Dr. Saqib. It's really interesting topic. I want to ask you, how do you evaluate the competency of this product compared to fossil fuel in terms of unit price?
In terms of?
Unity price of the final product. And it could like help like for developing countries. I think it would be very expensive for them. What do you think?
Yeah, definitely. This is also, I think, the same little bit relevant question from the previous one. So we are doing the techno-economic analysis. In that case, definitely we are also thinking about the price of the fuel. Right now, if we talk about the pilot scale, so our bio crude is definitely expensive than the fossil crude. So nobody will buy our crude because it's expensive. Why? Because it has some lack of calculations in terms of the energy calculations, in terms of mass and flow, so everything. So I think we are quite young in this research, almost 10, 12 years. So definitely with the passage of time, the research takes time. So definitely we will work out to minimize the minimum fuel selling price. I think it's the MSFP, like something like, it's a very famous term. So minimum fuel selling price, we have to consider this one for the comparison. Otherwise nobody will buy our crude. But one thing, if has the same price, we are then better than the fossil crude in terms of the emissions. So this is a green one. Okay.
Great,
Yeah.
that's a good answer. Thank you for that. And Dr. Sophia Ha, please.
Hi, Dr. Toor.
Hi.
This is Sophia from Department of Engineering. I think we emailed each other before. Actually, I recommend your name to the committee, and our Dean office finally invited you. So
Okay.
I enjoy your presentation very much. As you know, I'm also working in the field of HTL. So I have two questions.
Yeah.
The first one is you proposed that now you are working on this integrated process between this anaerobic digestion and hydrothermal liquefaction.
Yeah.
So could you please talk a little bit about these benefits? I'm thinking about after this digestion, I think the digest maybe consume the most carbon, and
Yeah.
maybe it's not an ideal feedstock for HTL. Could you
Yeah.
please talk a little bit about
Yeah,
that?
yeah, you are right, because most of the thing you will extract from the feedstock after production of the methane, the biogas, definitely. But we are also thinking about if we can mix other feedstock in this one, not only all the digestate. So for example, we have the digestate and also some other feedstock. For example, the municipal solid waste, which is not using in the biogas, or other agricultural residue. So as I mentioned in the end, it's a kind of synergetic effect. So we are not only dependent on the digestate in terms of the quality of biomass, but in terms of mixing with that residue with the other feedstock, then maybe it will be a kind of solution for this one. But this is again on the initial stages, not on the bigger scale. So we are just doing some parametric study on this one, because because the production and use of any feedstock putting into HTL reactor, definitely we look into the proximate and ultimate, we do the analysis to see the quality of feedstock. If it contains very low amount of carbon and hydrogen and these type of things, definitely it's useless to use in HTL. Same like in the way of the digestate. So I totally agree with you. I totally agree with you.
Okay, that makes sense. So
Yeah.
I should try that. You know, I have done a lot of work in cold liquefaction. Maybe I should consider this digested as one of the feedstocks.
Yeah. Cold liquefaction is only the possibility, not the standalone digestate. Definitely.
Okay, so that's my question. Okay, the second question.
Just before you do, Sophie, I just want to let the group know we're going to just continue on for 10 more minutes. So folks who have to go, feel free if you have to leave. But we're just going to extend a few more minutes since the talk allows us only now to ask questions towards the end, and we have a few in the queue, so we're delighted about that. Please, Sophie, sorry to interrupt, continue.
Okay. So all of us agree this HTL is amazing technology, promising technology, but in terms of commercialization and in terms of evaluating its economic viability, so would you like to share your thoughts of these kind of challenges that we have to face in this long way, try to commercialize it?
Yeah, definitely we have many challenges. The first challenge is definitely regarding, as I said before, it's a really energy intensive process. So if that process will be totally fail when you are putting much energy and you are getting very low amount of energy. Definitely, economic point of view, it's not the feasible process. But I think, as I said, by doing some kind of heat integration, by utilization of the byproducts and these type of things, and heat integration, I think maybe to some extent we can explore more about its feasibility. But if I have data regarding these type of things and information, definitely I would like to share with you.
Oh, okay. So I think your group is one of a few groups in this whole world who has tried this continuous process.
Yeah, yeah.
So what is the major challenge that you encountered in terms of a continuous process?
The major challenge is when you are working with high ash containing feedstock, so your system will block down. So for example, I think 1 year before we tried the sewage sludge. You know, the sewage sludge, it contains a lot of ash,
Yes.
and it will block your system because all the parts are very high temperature. So this is the first challenge if you are using high ash containing things.
Mhm.
And the second thing is the separation of water phase and oil phase. So it's
Yes.
also a challenge in our process. And another thing, I think the pumpability, because
Okay.
pumpability is very crucial, because if you want to get more energy conversion from the biomass, you need more dry matter in your water, not only 10% or 15%. But when we increased the dry matter content in our continuous system, so it's very hard to pump. And when you have very low, for example, if you take a glass of water, you put small amount of wood powder. After some time, it will be settled down. When you try to pump it, you will pump only the water, not only the wood. So that's are the challenging. So that's why we tried different recipes. We use some binding agents like CMC, crystalline methyl cellulose to make a uniform slurry. Sometimes we use microalgae, it contains protein and fat, to make a uniform slurry. So, but we did not successful in term of high dry matter, because only the pumpability is the problem. So you need a lot of power to pump 20% dry matter into your system. So these are some challenging in our system. And one time we tried the waste from the newspapers, the waste newspaper. It was also blocked due to some pigments and dyes and these type of things at high temperature. So definitely we have many challenge in term of the continuous system. So it's the pumpability, then your the dry matter content, and then your solids inorganic in your feedstock. Different feedstock had different ash contents. And the third one or fourth one, you can say, that is the separation of the water, because when we used sewage sludge, it was very hard to separate the layer between the water and the oil. So it's hard to distinguish. So that's our some challenges. It totally depends on the feedstock, totally depends, because some people use microalgae, very fine, and almost dry matter content, I think not more than 5%, and it super smooth run from your process. But when you will increase the dry matter, it will be problem in continuous system.
Okay, thank you. I appreciate your answer. Let's
Welcome.
keep in touch. Thank you.
Yeah, sure.
Great questions. Thank you for joining us, Sophie. And Mozamel, you had a question for our guest. Please go ahead.
Yeah, I have two questions I like to ask parallelly. Like, what is the near objective of biofuel? And next one is, are the engines are ready for the biofuel? Here I mean is like the generator and the machines that are ready to accept biofuel.
Okay. If you talk about the engine, so I think in Europe they are removing the engine, so most of the cars are electric cars. The first thing is this one. Okay. If we use the biofuels, in future. So it's the near future objective. I think we are not able to replace all the cars with the electric cars. Definitely in terms of the biofuels, we have to look at our environment, and we have to work on this one in terms of the emissions. So as I told, our biocrude from HTL process is not like the bioethanol and biodiesel, because for bioethanol and biodiesel, you have to modify your engine. But for the biocrude, when we upgrade it and when we do the hydrotreating and then distillation, so diesel, petrol, and the jet fuel, which I showed in my distillation cuts of the at different boiling point, those are exactly same diesel and petrol, gasoline, and jet fuel which we are getting from the fossil crude. So no need to change the car engine. So that is the future in terms of the implementation of a biofuel. And for Indian point of view, definitely in Canada, you guys also see a lot of Tesla and electric cars and these type of things. But definitely we also have to think about our CO2 emissions and these type of things. And by the way, for electric cars, for batteries, I don't think so. We have plenty of lithium and these type of material for all over the world to convert all the cars into the batteries. So definitely, we are just like peanuts, and we want to give our share in the society in terms of the green credits. Yeah. So this is the name of research. We have to do hard work. Maybe a time will come when we will succeed in a bigger scale.
Thank you, Dr. Saqib.
You're welcome.
Did you? Okay, I think, okay, and Persia, I think this might be our last question if we've covered off the others. So please, if you want to unmute yourself, welcome.
Thank you so much.
Welcome.
Yeah, so my question is, since you recently said that it's really expensive and it requires a lot of process to be actually feasible for people to use it. So in a simple term, I want to just know in a simple term, what are you going to do to make it more feasible in terms of your research? What are you going to include? Thank you.
Yeah, good question. So in terms of feasibility, maybe 100 and 200 years before, human being never considered that maybe they will fly in the air. But research takes time, then make the aeroplane. Now we are in the air. So the same thing we are doing. So we are doing research. We are facing the challenges. We are facing different issues. But in terms of implementation and feasibility, there is only one word in my mind, and that is optimization. If we are going to optimize our process in terms of energy, in terms of heat integration, in terms of energy and mass balance and everything, to make it more and more feasible. Because if you are going to sell your product or sell your technology to a guy who is a businessman, he will say, okay, how much money I will put and how much money I will get. That's the straight question. If you will say you will spend $100 and you will sell your product with the $80, so there is a loss of $20, he will never invest. So that's why we have to do the optimization for our process before we are going to sell our product. For this, we are working on techno-economical analysis and optimization and all these things, because in our field, we are not single player. We have the farmer and the agriculture residue. We have a municipal solid waste. We have to buy, we have to put the price our own biomass feedstock. We have to afford a very cheap feedstock. Then we have to optimize our process in terms of the energy intensive. And then we have to be enough smart to use our byproducts. That is our water phase, our gas phase, our solids as a biochar or as a fertilizer. So we have different areas in our process. So that's why the picture I showed with different PhD students, they are not only working on HTL. One is working on pumpability, one on reaction kinetics, one on optimization. One girl PhD student, Ileana, she is totally working on S1 Plus for the optimization of our process. She will never come to the lab. So she is working on the optimization and the economics and all these things. So we are working in all area. Yeah.
Thank you, sir. Thank you so much.
You're welcome.
Great. Well, I suspect there are other questions. I don't know if Dr. Sophia, if you have another one. Your hands up, but possibly you'll continue because you're already colleagues working. In
No, not on this situation. So we can talk later if I have any
You
questions.
can just send me email if you have questions.
Yeah.
Sure. We
Yeah,
keep
yeah.
in touch.
Yeah, definitely.
Okay.
You have very similar work. So you have touched on really critical issues for us, Dr. Saqib. And here we are, all of us looking to find ways to reduce waste, to be friendly with fuel, maximize it, to increase food security, as you said, and not demand more of land use, and to have clean energy that doesn't further add to the climate crisis we're facing. So all the work you're doing, we applaud you and your team. Great efforts. And we thank you very much for your time with us today. And we welcome collaboration. So thank you for putting that call to action out there. And I hope you'll have some postdocs take up that opportunity.
Yeah.
Thank you.
So you all guys are more than welcome to write me anytime.
Super.
Yeah.
Pleasure to have you join us.
Yeah, you're welcome. Okay, bye.